1916, Albert Einstein changed the way we think of gravity. You see, when Newton published papers on universal gravitation, people thought his equations solved it all. But then came Einstein. He suggested that space-time is warped or bent by any matter or energy. He continued by stating that any matter nearby will fall into this warped space-time. The question then is, what is space-time? Let's first explain the three dimensions. X represents length, Y represents height, and Z represents width. Now what space-time does is it combines space and it adds the element of time. Hence the name space-time. It is four-dimensional and it is very difficult to graph or display. To describe general relativity, we can refer to the Einstein field equation. It looks complicated, but we'll break it down. On the right side of the equation, we have some constants. They include pi, Newton's gravitational constant, and speed of light. T mu v is known as the stress-energy tensor. It describes how mass and energy are distributed throughout the universe. Let's move on to the left side of the equation. It describes curvature of space-time. The first variable, r mu v, is known as the Ricci tensor. It describes how much space-time is curved when one dimension is bent into four dimensions. The next value is r for the Ricci scalar. It describes the volume of a geodesic ball. The next term is little g for the metric tensor. It just basically allows you to describe from getting from one point to another through the curvature of space-time. The last variable is known as the cosmological constant. Nowadays we know the universe is expanding, but before Hubble discovered this, people believed that the universe wasn't changing at all. So Einstein fixed the equation as shown. To give an overview of the equation, we can say this, that the right side expresses mass and energy, and the left side describes how space-time curves. We can say this, matter tells space-time how to curve, and space-time tells matter how to move. We can replace the left side with g mu v with the right side being the same. This is known as the Einstein Tensor. What fascinates me is that Einstein made these two distinct phenomena equal to each other. Thank you for watching. I just wanted to clarify what I mean by geometry in respect to the Einstein field equations. So, what we're normally used to is called Euclidean geometry. It refers to anything that can be drawn on a flat piece of paper. Let's say this triangle here. But what happens to be the reality is that the Einstein field equations requires more complex math to describe the curvature of space-time. So let's say I curl this paper up. That's what the complex math that's required.